Kind of logical sense. But of course, the final lecture will try to tell you how to go beyond and do more phases and see what general can we say. So the first part will roughly discuss the macroscopic limit and maybe the bootstrap, and these are the two references, which I think are the clearest one. And the last part will discuss moduli spaces and superconformal field theories if we have time. I think that I'll discuss for sure. Okay, so what's field intuition? Again, our setup will be a CFT in D larger than 2 and assume just a U1 symmetry, but again, generalization is straightforward. And take an operator that creates a state on the cylinder. And, well, the idea is pretty obvious. The spatial manifold in the cylinder is a sphere, but if you zoom really close, you should recover some sort of flat space state. And the idea is that, of course, if the charge is sufficiently large, this flat space state will be pretty much a good approximation for your state on the cylinder. So the question is, how do we formalize this expectation? And the way you want to formalize is saying that there is a limit, and we should take both the charge and the radius to infinity with some appropriate ratio of Q and R fixed. And somehow the question is, what's the power here of Q? And this is a non-trivial question in general. But there is a simplest option, which doesn't always work, but it typically works. And it is to take what is so-called macroscopic limit. So it's the limit in which you take R to infinity, or equivalent you zoom pretty much. And you take the but you leave the dimensionful quantity specifying the state fixed. So the charge density, which is Q over RD minus 1, will stay fixed. And the energy density, which is delta over R to the D, fixed. Okay? So notice I'm not assuming anything about delta beside the existence of this limit, because I don't want to assume the superfluid description. But in fact, it follows immediately that if this should stay fixed and this should stay fixed, well, then the only option is the charge density should scale like the energy density scales like the charge density with this power. Or equivalently, delta Q should be some coefficient times QD over D minus 1. Which, of course, is what we found for the superfluid, but in fact it's more general. It applies to Fermi spheres, it applies to Lyster-Nordstrom black holes, it potentially applies to strongly coupled phase, in which the chemical potential is finite. Okay, so what can we learn if we assume that this limit exists? Or what do we mean, maybe, by the very fact that this limit exists beside this simple relation? So the existence of this limit means that if I now compute or if I consider a 3-point function of an operator whose quantum numbers are order 1, so charge Q and scaling dimension delta, actually let me write it the other way around. This is just the OP coefficient over R to the delta on the cylinder. And in the macroscopic limit, this should become the expectation value of this operator in the flat space state. Okay? And this, of course, is fixed by dimensional analysis to be a coefficient times the chemical potential to the delta, or if you want equivalently, a coefficient times the charge density to delta D minus 1. Again, because in flat space you have a unique scale. So it could happen this coefficient is 0, but this is the only thing it can be. And this implies immediately that the OP coefficient has a certain scaling with the charge. Plus subleading. Okay? So we didn't discuss it, but this agrees with the effective field theory prediction. But here we are not assuming effective field theory, we're just assuming that some flat space exists. It doesn't need to be a superfluid. And of course, effective field theory, on the same time, effective field theory also predicts a bleeding correction to this formula that instead are not captured just by the assumption that the macroscopic limit exists. So also this formula formalizes for you what does it mean for a macroscopic limit to exist. Well, it could have happened that once you take R to infinity, all correlation functions of this sort go to 0, just because the OP coefficient do not scale with Q sufficiently fast. So in this case, the limit would exist and it's trivial. That's not what I mean. It could also happen that lambda O scales with Q with a higher power, and therefore this limit yield an infinite result, so C is infinite. And this means that the limit doesn't exist. The statement that the limit exists is that for all correlation functions of this sort, this expectation value is finite, and at least for some of them it's non-trivial. Okay. So again, this is very hard to prove, but on physical grounds you expect this limit to exist. What does it mean for a 4-point function? So for a 4-point function, the 4-point function is roughly something like this: Q O delta Q minus Q Okay, so as an example, let's take a 4-point function of a scalar operator of charge Q and the one of charge minus Q with the same scaling dimension, so it would be the conjugate in the large charge state. Now, the statement is that you take the macroscopic limit here. Now, you don't only, this is 1 over R to the 2 delta by dimensional analysis times some function of the two cross ratios that on the sphere are just tau and the angular distance. Okay. Now, to take the limit to infinity, I need to keep the distance between these two operators finite, because I want to recover a correlation function in flat space. And the angular distance, of course. So this means that I keep tau fixed, and the angular distance, which is just R squared 1 minus n1 and 2. So n is the unit vector on the sphere that gives me the angle, which I call x squared for a reason that will become clear, fixed. And the result is just a correlation function in flat space. On R to the D. So, yeah, maybe another thing which is worth stressing is that this limit involves taking an infinite family of operators. So it's not a limit within a single correlation function. Okay, questions on this? Okay, so just so you know that this limit, of course, I'm formulating everything on the cylinder because I have a dimension for scale, which is the radius, and therefore helps a lot my intuition. But you can also phrase the existence of this limit independently just by varying variance. For instance, for the case of 4-point function, this is just the statement that the limit q to infinity of q to the minus 2 delta times your 4-point function written in terms of cross ratios admit a limit of this sort. Okay. So I think in this audience everybody knows what ZZ bar are, so I don't need to define them. Of course, and the limit is finite. That's the statement. Finite and non-zero. Okay. Okay, so why is this useful? Well, this is useful because it provides for you an explicit map between correlation function in the terms of operators and flat space, therefore provides a map between CFT data and observables for a non-trivial state in flat space. And you can try to use this map to learn about either of two under some assumption. So relate OPs and to spectral density. Okay, so the idea is now I want to just show how to make this claim concrete. It's fairly obvious what you have to do. Here a 4-point function, and you know it admits a conformal block decomposition with just amounts at exchanging states in this channel. Here you have a 2-point function in flat space and you have a spectral density. So the conformal block decomposition of the 4-point function should be related in this limit to the spectral density in flat space. Yes, sure.
So this limit is highly non-trivial for me because you're considering infinitely many correlators. But then when you do the OP sum, then all the OP coefficients depend on Q.
Yeah.
So do you need some extra assumption on how this coefficient grow in Q to make this limit finite?
Yeah, we will see it. We will see now what are the scaling, but clearly the existence of this limit implies, at least at large Q, some approximate analyticity in Q. And in fact, that's the main reason why you should expect some analyticity in Q asymptotically at large charge, is because you should expect this limit to exist. It doesn't tell you, of course, that it's fully analytic up to what point, if it's just approximate analyticity, just a leading power in Q, that I don't have techniques to answer those questions.
Okay.
But yeah. But no, you're right. We'll have to assume something about OPs and about exchange at scale dimension. And somehow the idea is that sometimes you know about this object, and therefore this will make predictions for the blocks exchange here and the OPs exchange there. So that's what I think it's useful.
Thanks.
Okay. So let's do this in some detail. Okay, so now in the S channel, so the S channel, I guess everybody knows this, or is just plugging completeness here for the theory on the cylinder. So S channel doing this OP and this OP, but it's the same thing as plugging a complete set of state there. So the S channel, I should say, converges in tau and in these coordinates only for tau bigger than 0. Okay, so what operators do you exchange? Well, you should exchange the ground state with charge little q plus capital Q. So I'll separate this because it will have a different interpretation. So and this is its block. So here is the scale dimension, here is the spin of the block. Tau and 2 and 1. And the OP coefficient, we know it's scaling already because we predicted it from here. Okay. So let me actually restore the 1 over r to the delta. Then you have the other operators, and okay, for now I'll be agnostic. Okay. So there is a claim now Okay, so the claim is that in the macroscopic limit, so now these are complicated functions. I think most of you in this audience know much more about them than me. But there is a claim, which is that in the limit that I want to consider, these functions actually simplify. And what's the physics of this? So each of these functions corresponding to exchanging primary in that identity decomposition, then descendants, then side level 2 descendants, so forth, so on. But the idea is that in this limit, only the primaries contribute. We will prove it in a moment. Plus order plus some reminder that I'll justify in a moment that it's small in this limit. Okay, so it's a nice exercise, so maybe it's worth doing the proof. And this was first noticed, I think, by Jaffaris, Mujanov, and Zhiboyadov. And I think Sridip and the collaborators have at least 2 proofs of this statement. There is maybe a third one in my thesis. It's very simple. Okay. So blocks at large Q. So what is a conformal block? Conformal block is schematically this object. O minus Q delta, tau, and 2, P to the n, delta L, K to the n, O delta Q, 0 and 1, Q. Okay, so roughly, you know the conformal block exchanges primaries and its descendants. That's what I'm writing here. But this is not the full expression, crucially. You also have to divide by the norm of the descendants. So the norm of the primary you can normalize, but then the norm of the descendant is fixed. K to the n. I'm neglecting spin indices because they are irrelevant for this argument. Okay, so you just have to remember 2 things. The first, you should remember the conformal algebra. It tells you that P2I to K is 2ID minus J, angular momentum. And therefore, this norm, so now you want to evaluate this norm, you just do it by repeatedly commuting these objects. And this norm just goes like delta to the n. Okay? So you have just n commutators. Let me just write x for simplicity. Okay? The other objects you want to evaluate is this or that equivalently. You know what P is. Of course, you have to write it on the cylinder, but roughly, P is taking n derivative of this object. Now, the kinematic dependence of this object, okay, you might want to remember what's a 3-point function in CFT. But actually, this is just an object, an expectation value of an operator at time tau. So you just use the evolution operator. you pick this energy and this energy. So this is roughly e to the delta minus delta q tau over r, plus some kinematic dependence on the spin, which I can neglect similarly. So n derivatives will just bring to leading order something delta q minus n, or L to the n, or some combination of the ratio. Okay, now you're done. You apply this estimate here, this estimate here, this estimate here, and you conclude that the nth level descendant scales like over delta to the n, or well, and some function of L delta minus q. Okay. So now I have to declare which delta contribute in the macroscopic limit. So first, are there questions on this? I think this is. What? I didn't understand it.
Is the asymptotic formula large delta or large n? Large delta, right?
This is large delta. So the point is that when you use these estimates, that this delta, I'm looking at heavy states, so this delta will be huge, but the difference, as you already imagine, here will be smaller. Okay. Okay, so if you don't care about the proof, you can still understand the statement, I think. Well, the point is that's. Can you repeat the question? So Slav is asking what's going to happen when delta is equal to twice delta q. And of course, well, that's a case where this is not suppressed. But the claim is that this is not the operators that contribute in this limit I want to look at. So let me, this claim is obvious, but let me explain it. Well, it's obvious. I think it's reasonable at least. So look for a moment at the dependence here of the block. So the dependence here is tau times the energy difference and a Gegenbauer, which you can roughly think as a plane wave in some sense, divided by r. If for d, there is a precise formula that relates this to a sign. So what's the intuition? Now I want to keep tau fixed and the distance fixed. But then this delta minus delta q should compensate the power of r here. So this means, and the same thing for L. L should become a momentum and should compensate the power of r that appears in the distance. So in the macro limit, only operators with delta minus delta q of order r and momentum, so angular momentum of order r, contribute. And if you remember the scaling of q and r that I unwarrantedly erased, this means that they scale like q1 over d minus 1. And this is q1 over d minus 1, both of them. So now you can look back at the remainder. Therefore, delta minus delta q square. So the point is that this will be some roughly some energy. So r omega minus delta q. So this is r. Sorry. Yes? Delta, yes. So this is, but now I'm saying the difference. So delta q, if you remember, delta q was going like r to the d. So it's much larger. So delta is roughly delta q in light of this equality. So let's do another step. Thanks. Over delta Q. And this is, again, in powers of R squared RD, which drop to 0 if you take R to infinity, and D bigger than 2. So, and the same thing you can get convinced with the angular momentum. So a beautiful fact, therefore, is that in this limit, you might have been confused. Maybe it's hard to relate CFT data or operator mass spectrum with CFT data of primaries because there is all the mass of the descendants. But this argument says actually that this is not true, and you actually only retain primaries in this limit, and you can make very precise statements. Well, very precise within our assumption.
You're estimating a single conformal block. What about the possibility of large degeneracy?
Well, I mean, this is about the kinematic dependence, right? So this is about this factor here.
Yeah,
It's like
but
a
you
filter
use this to argue for the range of delta where these operators are important, and you don't want it to be too much bigger than delta Q. But what if there's large degeneracy? So that, how do you know that there's no large degeneracy?
But I mean, I think this has nothing to do because I can always. This is about the scaling of the OP up front, which I haven't discussed yet. And it could be that this blows up so fast that this limit doesn't exist. My assumption this doesn't happen. But typically there will be large degeneracy actually, because here, so typically the two-point function in the flat space is dominated by a continuum in a strongly coupled phase, unless you are at very low energies. And so here it means you will have many radial trajectories contributing, but with some average OP coefficient that makes the limit work. The kinematic dependence I don't think can be affected by degeneracy, but it's just the fact that this should reproduce some Fourier transform with omega order 1 over tau. I don't understand how can that enter.
If there's a large degeneracy for the descendants, there's also a large degeneracy for the primaries. So your point is that the descendants are suppressed.
Yeah, the planets are suppressed with respect to the primary.
Wait, but no, that's not quite the answer to my question because it starts with Slava's question about what happens when delta is a little bit bigger, let's say delta Q plus square delta Q, something like that. You are arguing that for those guys, the block themselves are suppressed, but I'm not seeing why the degeneracy of those primaries, say when delta is delta Q plus square delta Q, why the degeneracy of those primaries would be suppressed?
You're saying if there are heavy primaries but with huge degeneracy.
Yeah.
Well, I mean, okay, let me think for a moment. I mean, as long as you take tau on 0, I mean, those can be enhanced. Okay, the assumption, if you want, is that there can be power enhancement of higher primaries, but as long as you take tau on 0, they will never dominate in this limit. They will be, I think. But
that would be an argument against the first line you have there, right? That the operator that dominates.
If I understand correctly, the problem is the statement that delta minus delta Q should be of that order. But you say that follows just from the existence of this macro limit.
Okay, so no, I think, I admit I don't have a smarter answer. I was a bit naive. I mean, I'm just thinking, if you think of this as a spectral decomposition, it's clear that frequencies of order 1 over tau and moment of order 1 over x are what you should expect to contribute. I haven't thought clearly what does this imply, I should say. You might imagine very heavy primary huge degeneracy, which are maybe enhanced by some power, and maybe in some kinematic regime they dominate. So I admit I haven't thought clearly about that. I don't know if Sridip maybe has more comment. He's also an expert on this. I apologize for that. Okay, so now you can take the limit. Okay, so these are skipped some steps, but they are physically straightforward. So here you're exchanging the ground state. And we discussed that this is roughly the expectation value of the operator in the macro limit. So this will be the disconnected piece of the two-point function. Here, you have to rewrite the exercise now to rewrite this in a flat space friendly formula. So this is already in a flat space friendly way, just e to the minus omega tau. But this you have to rewrite the Gegenbauer as some average over plane waves, which you can always do. Maybe just as an example, in d equal 4, this is something like sine L theta over sine theta, I think. So it's already in a friendly form somehow. But OK, you can do it in any dimension. And this was done in the paper already said by Zors, Ridip, Mark, and Avia. And the result is that this 4-point function becomes this. OK, I'll explain turn by turn. OK, so the leading term is the expectation value. There is this annoying phase up front. It's just a consequence of having a limit with a finite chemical potential. It's typical amount. If you want, you can erase it if you evolve operator with h minus mu q rather than h, but the natural limit evolves operators with h. But it's typical of finite density phase, so there's nothing to worry about. E to the minus omega tau, e to the I kx, modulus of k. OK. So the non-trivial statement is about this guy. This is some normalization which depends on the number of dimensions. Sum over delta L. And here you see how your OP coefficient should scale with R. R to the 2 delta, I think plus D minus 3. And this D minus 3 came out of the came out essentially of the Gegenbauer once you take the limit. Delta omega minus, OK, just let me write a bit. Delta minus, OK, delta Q plus Q here you have to put to be precise. Delta K minus L over R. OK, so this is a straightforward exercise. And OK, this relates spectral densities. And the relation to the spectral density that you all know is the following. This is roughly the spectral density in flat space, which is, of course, defined as sum over n, and neglecting 2 pi's, mu O delta minus Q, and O delta Q, mu, and the delta function in energy and in momentum, P minus Pn. OK. So this is a cute formula, and it's very neat. So, OK. Are there questions at all on this? Well, I mean, like in the, for instance, in the, yeah, so you can test this formula. So let me just make an example, and then I'll tell you where you can verify it. So if you imagine that rho omega k is dominated by a single particle, delta, let's say it's a sum over single particle, omega minus omega and k, where these are dispersion relations that someone gave to you, then you can conclude that there are Regge trajectories with delta equal delta q plus q plus r omega mu of L over R, and OP coefficients, since you need to erase this factor 1 over k, going like L. And so I was asked whether this formula can be tested. And well, for instance, in the first day, we studied the large charge operator in the epsilon expansion, and we know how to study the theory at finite density. We know that at weak coupling, you're dominated by single particles. So then you can ask, do the operators that I see on the cylinder have this sort of Regge trajectories? And it's just taking a flat space limit of the spectrum formula that we found. So, but this is more general, but in the case of triviality. So this is a case where you can check explicitly. Okay, so okay, another application of this is T-channel crossing. So what is T-channel crossing? So now we want to understand what does. So now you can go back to your 4-point function flat space for a moment. Zero and 1. And in the macroscopic limit,
Gabriel, just a basic question. I didn't understand this first formula. K of omega, K of minus omega.
yeah, I didn't justify it.
Don't you only have positive omega here in this formula? Or?
Okay, so let me think for a moment. Yes, but so the relativistic spectral density, I think, also picks. Okay, where does this come from? Let me remind. I think the intuition, okay, so is that this is taken from the commutator. So in the relativistic case, this could be something delta omega square minus k square.
I see, because you're on top of an excited state, an
Yeah,
of...
so I think, well, no, I don't think you can get negative omega. I'm trying to remind myself why you need that other factor. Yeah, so I think because when I define this, I should put an absolute value here. I think that's the issue, so thanks. So if I have to put an absolute, if I want this formula to be valid for plus and negative tau, I need to put an absolute value here. But then I also get some negative omega contributions here. I think that's canceling, it's the other way around. So I think the derivations is really papers somehow. And, right, so, yeah.
Okay.
But I mean, roughly, if we can, but okay, for the sake of want to be schematic, you can forget about this factor, and this prediction kind of follows simply. So, yeah, I should have been more precise. Okay. So now I want to study this OP. Again, this OP. So what does this OP tell us? This OP converges when these two are very close. So it should tell us something about the large delta operator exchange in the S channel. So that's what these Tauberian works are about. This is typically tough work to relate, to isolate the contribution of the primaries and get formulas for the sum over heavy states weighted by the OP coefficients. But the idea is now we have the macroscopic limit, And okay, maybe you can complain it's not fully rigorous, but within these assumptions, I already threw away all the primaries. So I can actually give a rather neat formula. So in the macroscopic limit, this is just the expectation value of these two guys. X O delta Q0. And if I do this OPE, the OPE contains a number of light operators. So this will be the sum over, say, delta tilde, L tilde, or a char of order 1. And okay, let me neglect spin indices. Lambda delta tilde, L tilde, and the expectation value of the operator at finite chemical potential, which of course is roughly mu to the delta tilde divided the distance, 2 delta O minus delta tilde. So you roughly get a sum of this sort. Lambda delta tilde L tilde x mu to the power delta tilde x to the power 2 delta O. Okay? So from this, you can extract an asymptotic relation for the spectral density. In the thermal case, this has been discussed a lot. For omega to infinity is something like sum over delta, O delta, lambda delta, again neglecting spin indices, omega minus delta tilde, I think. Well, there is some factors, actually plus 2 delta O minus D. And therefore, okay, so what does the macroscopic limit bias is that now you know this is related to this K as well, and therefore you can get a prediction for these OPEs. You might be confused because that's a continuous formula again. This is a discrete sum. So the statement is that this formula here will apply if you average your K omega K that I defined before, K bar, with some distribution of which, let me call it with L omega bar, K minus K bar, where this L is of order 1, and therefore if you average your OPEs with some smooth, this could be a Lorentzian, I don't know, just to make an example, something like omega minus omega bar square, K minus K bar square, say plus L square, and then and L, something like this. If L is large enough so that you pick sufficient down contribution of operators, this formula should hold. I suspect this can also be made into a rigorous Tauberian theorem, but that's I haven't worked out, so this needs to be understood. Okay, so questions on all of this? Okay, so this was about the macroscopic limit. So I should stop at 10:45, right? Or okay, so I was hoping to discuss a bit the large charge bootstrap, but I think the discussion so far has been fairly technical. Maybe I can just discuss moduli and finish a bit earlier, so everybody gets some rest. So it's more conceptual, so maybe it's more interesting. Okay. Okay, so let me just say for everybody's education that there is also, so this macroscopic limit helps us analyze the ST channel, to give at least a physical interpretation of the ST channel crossing just by OPEs in the finite density state. But okay, now you want to ask about SU channel crossing. And Zhiboyedov and collaborators analyzed it. And Turns out it's a bit more subtle. You have to make some assumptions. But they could prove that within certain assumptions, in particular that only certain number of radio trajectories contribute to large charge, the superfluid is somewhat the only solution to that crossing. Of course, the assumptions they made rule out other obvious candidates, like Rice-Randolph black holes and Fermi spheres. So you might not, depending on you, I think it's interesting, but depending on you, it's another story. Okay, so okay, so let's start. Okay. Okay, so theories with moduli. Okay. Okay. So in this course, we discussed a lot this delta going like QD d-1 relation. But then every one of you might come to me, and I have my favorite supersymmetric theory or free theory as delta equal Q. So are you so strong that you can solve the auto model? You cannot say anything about free theory, at least conceptually. And well, it turns out that what's special about free theory, or about the supersymmetric theories that we all know and love, is that they have moduli spaces. So the setup now will be a CFTD with a moduli space where the internal symmetry group is partially broken.
We're using a method like
Yeah. I don't know where it going. Okay. So, so what does it mean to have a moduli space? It means that there is a vacuum that you can call V, in which operators acquire a VAV, but Poincare symmetry is preserved. So Xio V to the delta. So only scalar operators. Again, in free theory, it's obvious, and many SUSY examples. The claim from which I want to start is that the moduli space EFT is equal to the large charge EFT. Okay, so the existence of a modulus tells you right away that if you go to the vacuum where the conformal symmetry is broken, you must have Goldstone bosons. So the Goldstone boson associated with the breaking of the intercell symmetry, and the Goldstone boson associated with the breaking of the conformal symmetry. So the dilaton and the Goldstone. And therefore, you have an EFT on the modulus. Okay, often we know this EFT exactly from supersymmetry, but here I want to be very general. So on general grounds, and I'll focus on D equal 4, this EFT contains an axiodilaton. Okay. Let me just write it. Okay, I don't know what's going on with the pen. Where this is. Okay. So what have I done here? So the Goldstone bosons here include a dilaton, sigma, a U1 Goldstone associated with the Cartan of the internal group G, and the non-abelian Goldstones, so some pi A that I'm neglecting. And then the theory of the moduli space often has, in many examples, other degrees of freedom, which are sometimes also potentially strongly coupled. We could have some Argyres-Douglas theory inside, I don't know. This I generically denote by CFT-IR. another irrelevant contribution. And what I've done here is to group the U1 Goldstone and the dilaton in an obvious way. Plus I C pi. I cannot determine this C from EFT, but I know that but I can always do it. So I don't know, the fact that I cannot determine this C means that I don't know the charge of this pi in terms of the U1 charge of the UV. Huh?
I'm saying this is very cryptic. Can you explain this equation? Phi equals what? What is the e? Is it e to the power? Is it rho to the power?
So sigma x, pi x.
Yeah.
Okay, so let me.
What is the letter? You understand? Is it rho or e?
E. This is I. This is E.
Okay.
Sorry. Okay, so I mean, because I'm just saying from the viewpoint. Okay, let me just make it. If you're an effective field theorist, you write your EFT with a dilaton d for x e to the 4 sigma d sigma square. Then you write with some Wilson coefficient the kinetic term for your Goldstones, and then so forth, so on. You don't assume that there is a free field, right? This is what you would write as an effective field theorist. You just write a shift invariant scalar and a dilaton. So this is also again in e to the 2 sigma, and so forth, so on. I'm just saying I can always group pi and sigma in a unique axiodilaton field. That's the only thing I did. But when you do that, you pay the price that there is this coefficient C, which means that you cannot declare what's the charge of phi in general. So, but okay, sounds irrelevant, but okay, when you want to make predictions, you want to know what's the exact charge of phi. That's the only thing. But okay, so just to say that there is an axiodilaton. Maybe this is too stupid. Okay, so, and the EFT typically holds when phi has a VFV. Okay? So another comment that I want to make, I like to make, even so it's not really related to the charge, is that the EFT on the modulus are kind of funny. So typically, if you assume spontaneous symmetry breaking of an internal symmetry, you write all the terms consistent with the symmetry, and the EFT is self-consistent. Instead, if you do it on the modulus, and you don't assume anything else but conformal symmetry, you find that there is a term that you can write, which is just a potential. And this is the reason why moduli spaces are interesting, because they're non-generic, because the EFT by per se is not self-consistent. Okay, let me not say more. So what happens, of course, why they're interesting, because we know many supersymmetric examples where you can essentially relate the phi to the 4 coupling to a Yukawa, and it's easy to kill a Yukawa with discrete symmetries, or sometimes even if you have extended supersymmetry, then you can say do even more. Okay. Okay, so a general comment, however, of course, if you have an effective field theory, pretty much like gravity, of course, you're not forced to expand always around the same background. You can expand around any background as long as the derivative expansion is good. So it means as long as the derivative of phi are much smaller than phi itself. So there is an obvious solution, just because the theory is free to leading order, which is the following. And turns out the FT holds as long as V tilde is much larger than 1. And what's the meaning of this solution? I think you already probably know, since this is this course. You will rescale to R times S3. And the meaning of this solution is that it's just like a superfluid solution where now V, okay, so V is now V tilde over R. Okay. And so this solution is just the class of solution we've been studying all of the time. By the way, I mean, this condition holds everywhere but at x equals 0 to infinity, of course. But you can always catch your path integral. So this means in your EFT you can describe this solution, but this solution we studied to that is just a charge Q state. And therefore, if you just plug this solution back into your action, you get right away this result for the scaling dimension up to subleading correction that depends on irrelevant coupling and a coefficient which depends on the precise quantization condition. So roughly, the charge, just as to give a step, roughly the charge is I phi bar phi dot plus Cc, which means it's V square over R. This should be the charge divided the volume. So you see the charge goes like V square. Okay.
I'm totally confused. Shouldn't phi just be a constant? So why did phi start depend on x? I thought
So-
in the vacuum you said the value of phi is v, and that's
Okay,
it.
so I'm just saying, so when you derive this EFT, good. So thanks. So you derive this EFT starting from a vacuum like this. Okay.
Yeah.
So here we understand where this EFT comes from.
Yeah.
But so once you have an EFT, you're not stuck to one solution plus excitations. What happens in GR? You can derive it maybe starting from Poincare breaking, but then you find other solutions, stars and whatever. And the idea is that all these solutions are good as long as the derivative expansion is good. So here I'm just saying, let's look for another solution, this EFT, where the derivative expansion holds. So this will be another saddle point in my path integral where I expect my effective field theory to be valid. And this is a trivial solution because the action is free. It's just the free propagator of the scalar. And the free propagator of the scalar, just by the argument we'll be discussing a lot in this course, is that when you go in radial quantization, just describe this solution, which corresponds to a charge Q states. And now, okay, charge Q state in free theory, okay, I can do the calculation, but it's linear in Q, the charge. The only point is the quantization condition of Q, which enters the coefficient. Okay, so this gives an expected field theory explanation for what you all know, that free theories and supersymmetric theories have a delta Q linear in Q relation. But also I think gives more because it tells you that now the effective field theory in the modular space predicts its large charge CFT data by the usual techniques, or vice versa, depending what you care. Okay, so now when Q is equal to an R charge in extended supersymmetry, typically the relation is exact. Exactly. So you might say this is boring. All the theories I know have this relation now generalized into D-dimension exactly with a coefficient that I can predict. And one comment is, how does this happen in effective field theory? Well, this happens because the effective field theory then is constrained by extra supersymmetry. And some miracles that happens in this effective field theory is that typically to protected observables only a finite number of operators contribute, called F terms. So in that case, essentially you can prove there is a unique operator contributing to this and the result is exact. Of course, it's a fancy way to recover a result you know. But there are non-trivial examples instead, also. In 3D n equal 1 theories, in which this relation also has a asymptotically large charge, but since 3D n equal 1 theories have no holomorphy, the relation is not exact, and we checked it in a number of examples. So in this case, in 3D n equal 1, this goes like this, plus a Casimir energy, which depends on what is on the modulus, q to the 0, plus order 1 over q. So you might ask, how do we make checks in 3D strongly coupled theories? Because these are theories studied a lot in the context of dualities, but they're typically strongly coupled. Well, it turns out that these theories admit an extension in 4 minus epsilon dimension, and you can make calculation. So that's nothing deep. But in this case, this is flavor symmetry? Yes, this is typically some flavor symmetry. So the modulus breaks some internal symmetry, which is not an R charge. So that's why it makes it interesting. Yeah, there is no R symmetry at all. Okay.
Gabriel, do you mind making some comment about the comparison of what you had before, which was basically following from dimensional analysis?
Yeah, I want to comment now about so I think Joe is asking, said a lot that this relation delta Q going like QD over D minus 1 follows from dimensional analysis or flat space limit. So how does the story fit into that? Well, this is precisely one of those cases where that macroscopic limit fails. I have to find a new macroscopic limit. And OK, so let me precisely discuss that. I think this is a good point to end the course. Actually, before that, let me make a comment. Let me erase. OK, so you might not care about too much about this 3D. Let me just make a comment about this formula, sorry, before. You might not care too much about this 3D n equal 1 conformal field theories. But there's been some interest in the literature recently in claiming that scaling dimension of charge operator should be subadditive. Now, in theories where the charge goes linearly at linear order in Q, subadditivity becomes equivalent to the negative, to the fact that the Casimir energy should be negative. This is motivated by the positive binding energy conjecture in holography. So these theories are candidate to test or disprove that conjectures, just because you have to prove that this Casimir energy should always be negative. OK, so this is something that might be of interest. 3D theories with modular SP. Yeah, so like just, for instance, superpotential like this. Well, there are many examples. Let me remember the notation. So this is maybe the most famous, but there are many others. So this is n equal 1 notation, so this is d2 theta. And the main point is that d2 theta under time reversal is odd. So this puts some constraints. M is a SU2 doublet. And R is a triplet. These are all n equal 1 superfields. And the modular space is at Ri, I don't know, like non-zero. So the main point is that these discrete symmetries force you to have an odd number of fields inside, but there is no SU2 invariant. So now you go on the modular space, this M become gapped, you integrate it out, and now you want to write a potential for R, but there is no potential for R, which has an even number of R, and it's at the same time, which has an odd number of R, and it's at the same time SU2 invariant. Anyhow, the point is, maybe it's fast, but the point is that here what saves is that you have these extra discrete symmetries, because the Majorana fermion shifts by Ni under time reversal. Said it very quickly.
If you don't require a global symmetry, there are, of course, many more examples. Like
yeah, we thought, but also with global symmetries, we have a plethora of examples all based on these discrete symmetries.
Sorry, I'm a bit confused. What are we calculating here? We are calculating the large charge operators of the,
yeah, so
the
here we would
center of the
calculate
modulus.
The scaling dimension of an operator of this form. N minus traces.
These are scaling dimensional operators of the center of the modular space, where it's.
Yes. So the idea is that this. No, we are calculating the scaling dimension of an operator in the CFT.
Okay.
And the idea is that this can be described in effective field theory, while the same effective field theory that describes the modular space.
Okay.
And this would be a charge n operator under the Cartan of the SU2 symmetry of this example.
I see. Thank you.
But okay, so okay, these are more interesting for me conceptually. But okay, I want to say something about the macro limit. Okay, so what's the natural way to take the infinite volume limit? Of course, you see it. So the solution, let me rewrite it, is to take R to infinity, but taking the VEV fixed now. So in this limit, the classical solution that we had, which is V e to the minus IT over R, this is 1 over R, so you don't see any more the oscillations in time. So this is the difference with respect to the standard superfluids. So the chemical potential is 1 over R, never becomes large. So in this limit, this just approaches V. And if you remember now that the charge density was V squared over R, or Q over R cubed in 4D, Sorry. Yes. So now the charge density in this limit drops to 0 because V is fixed, but V squared was Q, so this also tells you that Q scales like R in this limit. So not anymore R to some weird power. Sorry, Q scales like R to the 1/2, I think. No, sorry, what am I saying? Okay, sorry, I'm getting a bit confused. Have it here. Yeah. So V is fixed, and V is square root of Q over R. Yes, so Q scales like R to the 1/2. So the statement is that in this limit, of course, what you recover is the theory in the moduli space. So this expectation value in this limit just becomes the expectation value, where this is a generic light operator on the modulus. V to the delta O. Okay, so this relates OP coefficients and CFT data on the modulus. And the same thing for the 4-point function. X1, X2, Q becomes the 4-point function on the modulus. Okay, so I think this is interesting because this provides a map again between CFT data of heavy operators, of course, and CFT data on the moduli and data on the moduli space. Particularly the spectral density here is again related to some OP coefficients here. And sometimes, okay, the question is what can we learn about this? And yeah, I think this is a good question to finish this course.
Any other questions?
So then in this model, if you want to go to a finite charge density in flat space, you have to go to a further excited state. Is that a higher charge?
So the statement is that theories with moduli become tachyonic once you add a chemical potential. So in free theory, this is obvious. Well, it's simple to see. So if you start, say, okay, let me just. This is not the good one. Okay, I'll pick it up later. If you start with free theory, the chemical potential, which means to shift like this, the derivative, phi square minus nabla phi square. Then the spectrum becomes the relativistic spectrum. Actually, let me add the mass for a moment. K square plus m square plus minus mu. So charge plus and charge minus state split. So you see that when mu becomes larger than m, you get a tachyon. And in typical theory, the tachyon is cured by quartic potentials, but here you don't have it. So I think that there is no ground state with homogeneous charge. That's just a statement. There's no state which has homogeneous charge in infinite volume. You can take a finite volume limit, of course, and take this limit, but yeah.
Thank you.
Thanks. I can ask a question then. Yeah, just a quick. Do the gaplet boson you discussed, Goldstone boson you discussed yesterday, play any role in the
No, this is
spectral
much
density?
simpler. This is much simpler because here what you're using is the effective field theorem, the modulus, which is relativistic. So you just use the standard Goldstone theorem. So here you don't have to learn anything new.
So there is a long-standing folk conjecture that theories with moduli spaces, apart from free theories, they have to be supersymmetric.
Mm-hmm.
Do you, from your technology, do you get any insight into this statement?
No, I just related to the conjecture that Q is linear in Q, only in theories with supersymmetry or free. No, I don't think I got anything insightful, I'm sorry. At least that's the question which I wanted to, one of the questions which would be nice to explore. Sorry.
maybe some version of this question. Is there some property of the CFT data that would imply the existence of a moduli space? For example, if delta Q grows linearly in Q, does it happen in other examples or just in theories with moduli?
Okay, good. Well, implies a strong word. So within the realms of this macroscopic limit, you can ask imagine that delta Q goes like Q to the alpha. And now let's say what powers of alpha are allowed. So I think there is a claim that maybe I can try to reconstruct. So the claim is that if alpha is less than this power d over d minus 1, actually let's mean for d, that's less than 4/3, so we don't get confused. The only way to take the macroscopic limit, you end up in a theory with 0 charge density and 0 energy density. So this sort of suggests that you are actually in a theory with 0 energy density. So this sort of suggests that you have a modulus in that case, if you believe in that the macroscopic limit should exist. Now, I think you were asking for something more precise than this, and I don't know, but maybe this I can make precise. Okay, so the energy density we're assuming is like Q to the alpha R4 in 4D, and the charge density is Q over R cubed. And now you can try to take if there exists a macroscopic limit and the theory doesn't have a modulus, this macroscopic limit should end up in a state with 0 energy density. That's the statement. So now you want to take a limit where Q is like R to the 4 over alpha, right? Yes. So now if you use this limit here, you see that this goes like R 4 over alpha minus 3. So now if alpha is larger than 4/3, this goes to 0. So let me just make it. So this becomes 0 for R to infinity. If alpha is larger than 4/3, if I'm not getting the algebra wrong. Yes, because like goes like negative power, but becomes infinity if alpha is less than 4/3. So this means that the only way to take this macroscopic limit, if this limit exists, is to suppose that the energy density goes to 0 for R to infinity. But a state with 0 energy density should be a state which is degenerate with the ground state, so it should be a modulus. Of course, then you can ask, can I still keep the charge density fixed? And this would be a bit exotic theory with a modulus in which Lorentz is spontaneously broken and some physical, but I don't know how to rule it out.
But wouldn't you at least say that a necessary condition to have a moduli space is that the dimension should scale linearly with the central charge for large Q? For the Q for large Q.
Yes, I would say that if you have a modulus in which one Cartan generator is broken at least, then that follows by the argument I said. Essentially because I'm proving that for you in the patinter there is a saddle point which scales with that energy. There may be another dominant saddle point. It would be exotic because it shouldn't dominate the infinite volume limit, but it should be either Q or less. So
at least in the case with charge, I think that's a nice result.
Yes. Thanks.
Anything else? Okay, if not, we can thank Gabriel again, and in half an hour we'll start again at 11:15.